The formation of planets around a star is a very complicated process, and until a few decades ago we didn't have a clear idea of how it could happen. Now we have a fairly defined general picture, although many details remain to be understood. So let's try to understand how the formation of a planetary system occurs. Before continuing with the video, leave a like and subscribe to the channel to stay updated on new videos. Until a few decades ago, it was unclear how planets could form around a star and how common this phenomenon was in the universe. Until the mid-20th century, one theory suggested that when two stars passed very close to each other, some material could be stripped from one star to the other, and this material could then condense to form planets. Naturally, in such a scenario, also known as the catastrophic theory, the event was quite rare because it's not easy for two stars to pass so close to each other. Today, however, the most accredited hypothesis is another, completely different one, called the nebular hypothesis. This hypothesis suggests that planets form from the material surrounding a star after its formation. In the nebular hypothesis, everything begins with the formation of a star, a phenomenon that occurs within large clouds of gas and dust called giant molecular clouds. These are very large clouds, sometimes tens of light years across, containing hundreds of thousands of times the mass of a star like the Sun, mainly composed of hydrogen and helium, the two most common elements in the universe, but also traces of other heavier elements formed in previous generations of stars. At a certain point, an instability occurs that causes smaller, denser regions of these molecular clouds to form even denser clumps. These clumps begin to collapse under the force of gravity, becoming increasingly dense and hot. Over time, the central part of these denser regions heats up enough to trigger nuclear fusion reactions, leading to the formation of a star. To understand the formation of planets, however, we are interested in the material that remains around the star after its formation, a tiny part of the initial nebula because most of the mass goes to form the star. One thing to keep in mind is that when gravitational collapse occurs, the cloud is not perfectly static but always has a small rotational component, and gravitational collapse amplifies this rotational motion. This phenomenon can be understood in two parts. First of all, when the cloud condenses, the rotation speed increases, similar to a skater who spins faster when she pulls her arms in. The second thing that happens during the collapse is that this rotational motion causes the cloud to flatten along the axis of rotation, similar to when pizza dough is spun and becomes flattened, forming a sort of disk. The initial nebula, which initially has an irregular shape, over time forms a star in the central part during the collapse, but the material that remains around takes on the shape of a disk. This phenomenon, the formation of a disk from collapsing rotating material, is quite common in the universe, and is the reason why, for example, spiral galaxies also have a flattened shape. In short, this disk of material surrounds the forming star and contains the ingredients from which planets will form, called a protoplanetary disk. Another thing to keep in mind is that for planets to form, it's not enough to have just hydrogen and helium, the gaseous components of the disk. There must be rocky material as well, meaning small grains of dust that can be metals or other heavier elements formed previously in the universe. These dust grains over time collide due to the chaotic motions within the disk and begin to adhere to each other, forming grains that grow larger and larger. This process takes a few 100,000 years and first leads to the formation of what are called planetesimals, which are rocky objects a few kilometers in size, which then further grow into protoplanets, about 100 or so objects the size of the Moon or Mars. From this point on, what happens is that the orbits of these protoplanets are very chaotic and occasionally intersect, causing very large and powerful collisions that lead to the formation of even larger objects. This process takes a long time, hundreds of millions of years, and in the inner regions surrounding the star, it leads to the formation of rocky planets. In this regard, it should be noted that in the inner regions of the protoplanetary disk, those closest to the star, the temperature is very high and only materials that do not easily melt or evaporate, such as metals and rocks, can survive. These elements are generally quite rare in the universe, so the rocky planets that form in this way are not very large. In the more distant regions from the star, where the temperature is lower, elements that evaporate more easily, such as gases and ices, can survive. These materials provide additional building material for forming planetary objects. The distance in the protoplanetary disk beyond which the temperature is low enough to allow the presence of ice is called the snow line. Not because there is snow, but because icy material can be present. In the outer regions, therefore, beyond the snowline, planetesimals and protoplanets can be larger because there is more building material, and the gravity of these objects can also attract the gas that remains in the protoplanetary disk, leading to the formation of giant gaseous planets. This is the general picture, very simplified, of course, but there are many reasons to believe it is correct. There are several pieces of evidence pointing in this direction. The main one is that in recent decades we have observed protoplanetary disks. The instruments have become powerful enough to actually see the disk forming around new stars. Furthermore, the nebular hypothesis explains why the planets are all in the same plane. This is something we have seen in the planets of the solar system, but is also observed in other planetary systems. People often ask why all the planets orbit in the same direction and on the same plane. Well, this plane is the plane of the protoplanetary disk, and the orbits of the planets follow the initial orbit of the material in the protoplanetary disk. The nebular hypothesis also explains the differences in the composition of the planets, at least qualitatively. The reason why smaller rocky planets are found close to the star, while gaseous giant planets are found in the outer regions beyond the snowline. However, some details are still not well understood, and perhaps the main detail is the formation of giant gaseous planets. The formation of giants is a complicated process. There are various scenarios imagining how gas can be accumulated around the giants. One of the things that has changed the way giant formation is viewed in recent years is the fact that many of the systems discovered around other stars have giant planets very close to the star, something that does not happen in our solar system, where all the giant planets are in the outer regions. However, in the statistics of discovered exoplanets, so-called hot Jupiters, giant planets very close to the star are often found. The idea is that these giant planets did not form close to the star, but migrated from outer orbits towards the star. This hypothesis is still under study. The process is complicated and could influence the architecture of planetary systems. Systems that have had giant planets migrating inward may not have rocky planets, whose inner orbits may have been disrupted by the giant's migration. These things require complex numerical simulations to be better understood, taking into account all the physical factors leading to the formation of a planetary system. To better understand the formation of planetary systems, it is useful to study our solar system, including asteroids and comets, which have remained almost unchanged since the early stages of formation. We have understood that the formation of a planetary system is complex and chaotic, with much variability and general regularities. Planetary systems evolve over time, changing characteristics with the evolution of the star hosting them. By better studying the solar system, observing protoplanetary disks, and analyzing the composition of different planetary systems, we will continue to clarify the general picture. We have made much progress understanding that the formation of planetary systems is common in the universe. Today, we think that almost all forming stars are surrounded by a disk of material leading to planet formation. Thanks for watching. Remember to subscribe to the channel to support us.